worse time and lower is better time. All right? Then, if you look at the minimum heap size, semi-space is poor because it is reserving half the heap, but you can see that the mark sweep isn't that great. Like, it's okay, but it's not like very, very close to mark compact because of size class issues. All right, and then when you put it together for total performance, we get mark sweep as being the state of the art, 20 years ago, or 15 years ago. So now we add in IMIX, and it gets the same locality as the other bump pointer, not surprisingly, because it's using the same mechanism, although it's a little worse because of skipping over lines. But the garbage collector is mostly just tracing, and so that's just as fast and slightly more space efficient than mark sweep, so it runs in a tighter heap. So you can push it over further to the left, and then its space efficiency with opportunistic copying makes it very close to compaction, which we were delighted and a little surprised about how well it did there. So then it's at the bottom, all right? Now, let's go to generational GC. So everybody's using that bump pointer semi-space in their nursery. And why are we doing the nursery? Because in 83 and 84, several people noticed that young objects die quickly, and so you can get a lot of memory back if you collect it in the nursery first. So what are the ideas? You bump pointer into the nursery, then you trace out the live objects and you put them into an old space. I'm showing a copying old space for simplicity here. And then you fill it up again. But the rub is you have to do some more work in the mutator in order to do this. Because in order to independently collect that nursery and find all the live objects, you have to know about any object in the old space that's pointing back into your nursery. So that requires a write barrier. So a write barrier is a piece of code that goes on every single pointer write. And all garbage collectors that use multiple regions, so all modern generation collectors use some kind of a nursery, they all have at least a write barrier. That write barrier, in the case of can be pretty simple. In this case, it just says, am I in the old space? And you can organize the memory, so that's just a really quick test, like a barrier on range. And you can say, if I am, now a little more expensive, because most writes are actually happening in the nursery, but a few of them are happening in the old space. And then you can say, is my target in the nursery? And then you record it in a cross-generational pointer buffer, okay? So then you have all those pointers and you treat them as roots, okay? And you don't do anything smart there, so when you go to visit that object and see if that root, you have to see if that root is still live or still points into the nursery, and it may or may not. And you still have to process roots that point into the old space, but you notice, hey, this root points in the old space, so I'm ignoring it because I kept track of all the pointers into the nursery. Okay? So G1 is the most widely used collector today. It's the default in OpenJDK. It's a production GC that's called Garbage First. It uses a generational bump pointer nursery, and it evacuates into a free list old space. Okay? And it's a stop the world collector. On to parallel GC. Parallel. All the threads are busy all the time. Not really. So, parallelism is imperfect, all right? And if you try to run your cloud machine at 100%, your performance will suck, okay? So for a latency-sensitive application, you need to run at about 70% sold, or 70% utilization, and you need to, in order to handle bursts of activity that might happen. all right? So I'm going to draw solid lines from now on, but this is what should always be in your mind, okay? Just because it was easier to draw. All right, so here was our stop the world. The problem with it, those lengthy pauses suck also for latency for your application. And if you have new requests in your latency-sensitive application, like search, arriving while you're paused, their latency is going to be bad. So, yay, let's make the pauses smaller, okay? So the state-of-the-art in making pauses smaller are Shenandoah and ZGC, but what they had to do was add a read barrier. So you see all those, so I wasn't that concerned about the write barrier, and I've written, I think, 2 papers about write barriers. I think Steve has written like 6 papers about write barriers. So you can write and read barriers. You can make that write barrier pretty fast. You can't make read barriers very fast. They're always 5 to 10% performance hit. And why did they do that? Because they needed to make their pauses short, they needed to do concurrent copying while they were allocated. And because parallelism is imperfect, there are slots to run the concurrent GC threads in and do that copy. All right? But if we compare the G1 collector, which stopped the world that had long pauses, you get what you want in those, like G1's pauses are longer, okay? And that shows up it shows up here when we're just measuring how long the pauses are. So Shenandoah achieved its goal of smaller pauses. But what Shenandoah did not achieve was lower latency because of those read barriers interspersed. And this wasn't well understood until 2022. And their solution is to use lots and lots of memory. And that's like, that can be okay if you have extra memory on your machine or you're optimizing that. But for things like the phone, if you're paying Google Cloud for that memory, that you don't want to use all that memory. All right? So the rest at the top, like I just didn't do my time management at all. So how about tomorrow? I was going to give a different talk, but I'll give the rest of this talk tomorrow. All right? Thank you all so much for your attention.